Welcome to RF and millimeter wave IC design class. This is lecture number 10, and so far in the previous 9 lectures, if you remember, we started by talking about two different issues in RFIC, and we told that one is related to non-linearity and another one is related to noise. So both non-linearity and noise will be covered in Unit 1 itself. So for the previous classes, we looked at the effect of nonlinearity in little detail, and we observed the different nonlinear effects like harmonics, intermodulation, cross modulation, desensitization. Arrived at two specific performance metric or performance parameters. One is 1 dB compression point, and another one is third intercept point or IP3. And I hope you understand why we have these two performance metric. So 1 dB compression point will talk something about the linearity of of the circuit, and IP3 is basically to understand how much can be the third order intermodulation product. How much is a third order intermodulation product in a nonlinear system, and what will happen if the IM3 products amplitude are rising more than whatever is the prescribed or the specific values. So we understood about two performance metric, and today in today's class we are just extending the idea of non-linearity, because we know that whenever we consider a RF transceiver or any RF system, it is not a single stage that is processing everything. It is very clear that we do have a number of stages in an RF transceiver. Say for example, if you have a receiver part, you will have an antenna followed by front and some filters will be there. Then there will be a low noise amplifier followed by a lot of other components. It can be mixers, it can be some other filters, it can be amplifiers, some other amplifiers. So the transceiver, or especially a receiver is not a single stage, it is a chain of blocks, right? So whatever we studied so far with a single system can be definitely extended towards a single circuit can be extended towards a system where we have cascaded stages, right? So in today's class we are specifically IP3, the intermodulation performance metric IP3. How IP3 will be calculated in a cascaded nonlinear stage. I hope you are getting the plot why we are doing this cascaded nonlinear stage. So, cascaded nonlinear stages. So as I just mentioned, signals in any RF system will be processed not only by a single stage but through different set of circuit blocks or different stages. So I can broadly say that any signal which is passing through an RF system, signals in an RF system are processed by cascaded stages. So why that is important now to understand about cascaded stages? Because when we talk about performance metric, we should also know how these we have seen that there are different products coming at the output of a nonlinear system, and now from one system to the one output to the next circuit, or when the same set of signals, when it is processed through different circuit blocks, how will be the overall effect? That is what we are um, going to see now. So first we will see a mathematical version of that, and later we will see the spectrum and the exact components and the available at the output of nonlinear stages. So for mathematical convenience, I am considering only two stages in cascade. So what I am considering now is I am considering two such nonlinear stages. Right. So when I say two systems, this is your first system, Give me a while. Yeah. This is your first circuit. This is nonlinear stage, and this is again passed through one more stage that is also a nonlinear stage. Now, to analyze this better, I am just marking the input signal as x of t. Then the output of first stage. So generally output we call it as y of t. Since it is output of first stage, I call it as y1 of t, and output of second stage I am calling it as y2 of t. Right. Now, previously when we were writing the output components of a nonlinear stage, we use the coefficient alpha for everything. Now, since there are two stages, and to make a clear difference between both stages, I'll be marking all the components in terms of alpha here, and here all these components in terms of beta. Now, looking for the input components here. So at the input, again what I'm performing here is a two-tone test. I'm considering that there are two frequency components at omega 1 and omega 2. Both have equal amplitudes A, and that is what is available at the input of these cascaded nonlinear stages. And what I'm going to find now is what will be the combined IP3 of the system, right? So let me mark here the IP3 of first stage can be written as IIP3 of 1, and the second stage is IIP3 of 2 of stages individually. Or if I write in terms of AIP3, AIP3 of 1 can be written as under root of 4 by 3 alpha 1 by alpha 3, that is for the first stage, and AIP3 2 can be written as under root of 4 by 3 beta 1 by beta 3. This is for the second stage. So what I have written now is for both stages individually. Now, now what I'll do now is I'll be writing equations for y1 of t, y2 of t, and from the output expression how we arrived at IP3 of a single system. Similarly, we'll try to find the combined IIP3 of the cascaded system, right? First I'll write what is y1 of t. So y1 of t can be written as so this will be after understanding the mathematics of after having this view. When we go for spectrum, you will get definitely more clarity, so please hold on. I hope that you guys are listening to me. If you are listening, please put a yes in the chat box. So y1 of t is y1 of t can be written as alpha 1 into x of t, alpha 1 into x of t plus alpha 2 into x square t plus alpha 3 into x cube t. As we mentioned before, we are restricting to nonlinearity up to third order only. Now y2 of t can be now written as alpha 1 into, sorry, not alpha 1, y2 of t, y2 of t is actually the output of the second stage, and the input to that is y1 of t, so that can be written as beta 1 into y1 of t plus beta 2 into y1 square of t plus beta 3 into y1 cube of t. This can be extended up to many number of terms, but for the mathematical convenience, we are restricting only up to third order nonlinearity. Now, what we have to do here is, in order to evaluate IIP3, since we know that IIP3, the contribution of IIP3 is coming directly from the first order and third order terms. That is what we observe when we have written IIP3 for a single stage. From this, we will consider only to evaluate IIP3. We know that we have to consider only the first order and third order terms, first order and third order terms. So what I will do here is I'll just Yeah. So I'll write the final output y2 of t, because IIP3, if you want to write IIP3, you should know what is the final output y2 of t. So what is y2 of t? Y2 of t can be written as y2 of t, as we have mentioned before, it is beta 1 into y1 of t. So what is y1 of t? Y1 of t is coming from here. So can you guys just plug in this expression? I'm not asking you to do the entire thing, but can you write only the first order and third order terms here? By observation, is it possible to write first order and third order terms? Okay, you can try that. I'll also write it here. So when you plug in y1 of t here, the first order term will be alpha 1 beta 1 into x of t. That will be the only first order term, because whatever you do, the other terms will definitely have either second or third or even higher order terms, right? Plus now we should write the third order term. So third order term, one will be directly coming from yeah, so from this one will be coming, then you will have a multiple, yeah, one will be that and one will be from this, and then there will be a product term also. So if you write that together, it is alpha 3 beta 1. So alpha 3 beta 1 into x cube t. That is what I meant. So let me give a circle mark. The product of these two, alpha 3 beta 1 into x cube of t, plus plus uh, you have this term here, which is beta 3 into y1 cube of t, right? This term beta 3 into y1 cube of t. So that also will give you a term. So that becomes, sorry, it is y1 cube. That means you will have alpha 1 cube and x cube of t. So I'll write it as alpha 1 cube into beta 3. Then again x cube of t term will be with that. Plus you will have a product term of uh, x into x square, which comes here when you have the product term here will be in beta. So it is 2 beta 2 into alpha 1 into alpha 2. That also will have an x cube term. So that will be uh, these two coming in beta 2, right? So these, so I have written directly. So if you have doubt, you can definitely expand this and see which are the third order terms, right? Plus there will be a lot other terms, but as I mentioned, we will be considering only these two terms here. Now if you look at this, this is the coefficient of the first order term and this is the coefficient of the x cube term, and AIP3 can be directly written here because we know that AIP3 is under root of 4 by 3 into alpha 1 by alpha 3 in general. But now in our case, it is the first order term and third order term. So if I write in a cascaded stage, I can write AIP3 as under root of the same 4 by 3. In place of alpha 1, I have to take the coefficient of x of t, which is alpha 1 into beta 1 divided by, in place of alpha 3, I should take the third order term, which is alpha 3 beta 1 plus alpha, let me write in this fashion, plus 2 beta 2 alpha 1 alpha 2 plus alpha 1 cube into beta 3. So this is the IIP3, right? So this is how we represent AIP3 for a cascaded stage when you have two systems, two nonlinear systems in cascade. But now I'm just doing some operations on this and trying to get to another form. I'm just squaring and inverting this equation. The very first thing what I'm doing is squaring and inverting this equation. So why I'm doing so is I'm trying to express in a much more simpler formula, so that if you have cascaded many number of stages, how you can find the overall AIP3 of the system. So when I do that, that I'll be doing even some more approximations later. So it is 1 by AIP3 square is equal to, it is squaring and inverting. So square root will go and it will be inverse of this 3 by 4 into alpha 3 beta 1 plus 2 beta 2 alpha 1 alpha 2 plus alpha 1 cube into beta 3 divided by alpha 1 beta 1. Right. Now this is this I'm further considering AIP3 square is approximated as. Why I'm approximating is I'm just separating the terms in the numerator, since it is inside mode. It is not exactly equal to that, but still I'm using an approximation here, which is equal to beta 1 will get cancelled, so it is equal to alpha 3 by alpha 1 plus you will lose this term 2 alpha 2 into alpha 1 will get cancelled, beta 2 by beta 1, and plus the third term is alpha 1 square into beta 3 by beta 1. I hope you are following me what I'm doing with certain approximations here. Right. Now this is this I'm further simplifying this as doing little more simplification on this. So I'll write it as 1 by AIP3 square is equal to, I'm just taking 3 by 4 inside, and yeah. So if you are taking 3 by 4 inside, what will be your first term? First term is 3 by 4 into alpha 3 by alpha 1, right? So that can be further written as, yeah. So what I'm doing is I'm just yeah, looking at the first term, it is 3 by 4 into alpha 3 by alpha 1. That can be, otherwise that can be written as 1 by AIP3 1 square. I hope you will agree to this, because AIP3 1 is under root of 4 by 3 alpha 1 by alpha 3. This is inverse of this. I'm just replacing a square term there, plus keeping the second term, it has 3 by 2 into alpha 2 into beta 2 by beta 1 plus the last term as alpha 1 square. Then again you have beta 3 by beta 1 and 3 by 4 outside. So that can be considered as AIP3 2 square. Right. So this is one particular form what you can write, and doing little more approximation on this. So I would say now I'm just going to tell you that tell you one thing, and later I'll prove that shortly. So in this term, what you are seeing here, I'll say that in narrowband systems, if you have narrowband systems, the second term what I have marked here can be neglected. This term can be neglected. So if I'm neglecting this term, so you'll be wondering how I can neglect that. I'll show how that can be neglected by looking at the frequency components. So if that is the case, then I can write the AIP3 of the total nonlinear cascaded stage as AIP3 1 by AIP3 1 square plus alpha 1 square by AIP3 2 square. Now looking at the formula, what you can say here is the combined AIP3 of two nonlinear stages in cascade can be written as inverse square of the first stage AIP3 plus the gain square of the first stage divided by the square of AIP3 of the second stage. And this can be further extended as, if you want to write it for n number of systems, AIP3 square can be written as 1 by AIP3 1 square plus alpha 1 square by AIP3 2 square plus alpha 1 square into beta 1 square divided by AIP3 of 3 square plus etc. This is what we can have a general formula for finding the AIP3 of cascaded nonlinear stages. So I just want to clarify, I have made few approximations here. I have just directly taken the mod value and I separated the numerator, and later I have neglected the Second term, by mentioning that in narrowband systems, this term can be definitely neglected, and I'll prove that shortly. Right. Is this clear what I have done just now?
Yes, sir.
Yes,
All
sir.
right. Okay. So now, if this is clear, what I will do now is we will see the spectrum. So what we have done now is we have written the equations. Now let us see what will happen to the components at the output of first and second stage, and how we can neglect this. The second term, what I have told in narrowband systems, we can neglect the system. We'll see this graphically by directly looking at the components. All right. So, but now I will request you guys to definitely work on this spectrum and let me know the components coming at the output. Right. If I'm getting sufficient response, I will be completing this. If not, I'll just leave it. I'll be leaving this as a homework for you guys, and I'll be discussing this tomorrow. Right. The rest of the things remain same, whatever we have taken before. So this is a nonlinear system. This is also a nonlinear system. Alpha 1, all those things remain same. Now we'll quickly look at the products. Look at the frequency components here. Okay. So now at the input you have omega 1 and omega 2. Those are the input frequency components having amplitude A. Now, the first term, all the terms will be written with alpha, and the second term, all the coefficients will be written with beta. Right. So, can you guys draw what will be the output of first stage? So, we will again look only at relevant components, which can contribute towards the calculation of IIP3. Because if you try to draw all the components, then it will be a total mess that you know. Right. So let us see first what are the components coming here. When I say the relevant components, I am referring to this expression, the expression here, what I have written. Right. So can you guys try in 1 minute? If you have omega 1, omega 2 with an amplitude A as x of t, what will be which all components should be considered at y1 of t, and what all components will come at y2 of t? I hope that you are working on that. So I'll also help in this. So if you look at y1 of t, you will have the direct product. The first product will be alpha multiplied by this term. So I will mark it as the first stage output will be, maybe let me use a different color here. The first stage output I'll mark it as, don't exactly see the amplitude. It is not done appropriately. I'm not using the appropriate scale. Yes, Sharad, you have to write the fundamental and intermodulation components. Yes, I hope that is a question which you are asking. Yeah. So this amplitude will be, say this is omega 1 and omega 2, and this amplitude is very, we know that since it is A here, I'll be writing it as alpha 1 into A, understanding that this is the fundamental component at the output. Right. Now we are looking at the for the first order and third order terms at the output of the system, not at the y1 of t. But okay, so I'm just clarifying that we are looking at the first order and third order terms at the output. But now for those first order and third order terms at the final output y2 of t, if you have some relevant components as at y1 of t, which can be, see the components which are producing first order and third order terms at the output need not be the same first order and third order terms at the y1 of t also, right? So you have to consider all the other terms which can result in a third order term at the final output. So this is alpha 1a here, and if I draw So okay, let me complete this. So alpha 1 a, which is at y1 of t, will directly produce a first order term, which is equal to, this is again at omega 1 and omega 2 of t, which is equal to alpha 1 into a, which is multiplied by beta 1. That is the first term what we have written, right? Now along with this, uh, this will also produce a direct third order term, so that can be written like this. What is a third order term? Let me mark it here. So that will be somewhere here with the frequency 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1, and the amplitude will be alpha 1a will be there, that will be cubed, and the coefficient will be 3 by 4 into beta 3. If you have doubt, you can definitely verify this with the previous discussion part we made. This will be one term. All right. Now another term coming here will be sorry. Yeah. So the another term coming here is 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. Can I get the value of other product term which you are writing here? So what you can do is you can look at the equation what we have written here. So this is the equation. So the term alpha 3 beta 1 into x cube of t is what we have written here. Sorry. Uh, Alpha 1 beta 1 into x of t is what is written here. Alpha 1 beta 1 into x of t. X of t is nothing but a. Now you have sorry, you have this term alpha 3 beta 1 into x cube of t, and alpha 1 cube beta 3 into x cube of t. That is what we have written here, right? Yeah. Alpha 1 cube beta alpha 1 cube beta 3 into x cube of t is written. Along with that, you have this term also. Yeah. So one is 3 by 4 alpha 3 beta 1 a3. Yeah, that is right. I'm trying to write the same thing here. Sorry, the stylus is not responding. All right, sorry, stylus is not responding. I'm just I'll close the application and open again. Yes, all right. So the first term, which is 3 by 4 beta 3 into alpha 1 a the whole cube, and one more term which will come here is, so before drawing that, we should also see the the term which is causing that product. So that is actually coming from the first stage output. So let me draw that first here. So which is the 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1 term, which with amplitude 3 by 4 alpha 3 a cube, which is the direct third order term of the first stage, is now bringing you the another term at the output here with amplitude 3 3 by 4 alpha 3 a cube into beta 1, which is a the third order term at the output of first stage, but directly multiplied by beta at the output of second stage. I hope this is clear. So if you look at these terms are already considered. So this is the only first order term, and these are the two second order terms what we considered. Now apart from this, you could also see that there is another term with 2 alpha 1 alpha 2. So let us see how you are getting that term. So if you look at the output of first stage, we have even second order intermodulation terms coming at omega 2 minus omega 1 with an amplitude of alpha 2 a square, right? So you have alpha 1 a, along with that alpha 1 you have alpha 2 a square. That is one term coming there, which is the IM2 product. Along with that, you have second harmonic terms coming in. Second harmonic terms are available at both with amplitudes alpha 2 a square by 2. So what I'm explaining now is the term what we have here. So let me mark this with this color. I'm talking about this term. The other two terms we already verified. For that third term, I'm considering the IM2 term at the output of first stage, and also the harmonic terms at the output of first stage. Now, when these two get combined, you will get products at the output of second stage at, so you can mathematically verify this. You will get product here, one as 2 omega 1 minus omega 2, another one at 2 omega 2 minus omega 1, each with amplitude of alpha 1 alpha 2 a cube into beta 2. This will be 1. So when you multiply these two, alpha 1 alpha 2 a cube into beta 2, similarly you will have one more term coming at the output here, that is also at with this at the same frequency, 2 omega 2 minus omega 1, that will have an amplitude of alpha 1 a into alpha 2 a square by 2 into beta 2. I don't know whether you guys understood this or not, how you are getting these terms. So it is a mixing of two terms, which is at the fundamental frequency omega 1 and IM2 term, that will lead to 1, and in second harmonic term and the fundamental term will give rise to the other one. So even let me mark that here. Whether this is clear, what I'm drawing here, whether it is clear or you have doubts in this. So we have the fundamental terms omega 1 and omega 2 with amplitude alpha 1a, and this is again alpha 1a. The product term, uh, the 2 alpha 1 alpha 2, the term which is available at the output of second stage is actually the product of these two, the sum of product of these two. Or I can just write the mathematical equation here for you guys to have a better understanding. So it is 2 beta 2 into alpha 1a cos omega 1t into alpha 2a square into cos omega 1 minus omega 2 into t. So this will lead to one product, and the other one is 2 beta 2 into alpha 1a cos omega 1t multiplied by uh, the second harmonic term cos 2 omega 2 t. So together these two will result in the final product what you can see here. So both amplitudes are same. This is alpha 1 alpha 2 a cube beta 2. This is alpha 1 alpha 2 a cube by 2 into beta 2. So if you combine these two, you will get it is like 1 plus 1 by 2, it is 3 by 2. So the term what you will get will be 3 by 2 into alpha 1 alpha 2 beta 2 a cube into the other term which is cos 2 omega 1 minus omega 2 into t plus cos 2 omega 2 minus omega 1 into t. I hope that you understood what I meant by writing all these equations. Can I get some response in the chat box? All right, yeah. So I got one response, but definitely it may take some time, but please take your time and analyze it again. So what I was telling is, this is very clear. This is straightforward. The alpha 1a component at the output of first stage, and directly it is multiplying with beta 1, and you are getting the fundamental term. That is fine. Now the IM3 product at the output of first stage, when it is multiplied by beta 1 and with cubic beta 1 and x cube t, that you will get these two terms. That is also almost straightforward. Now the product term, or the third term at the output of second stage, which is coming, or which is produced as a result of mixing of the fundamental and the IM2 term at the output of first stage, and fundamental and second harmonic at the output of first stage, is actually giving you the third term. That is what I have shown here, both graphically as well as mathematically. So now if I continue to write the expression, I will write it as y2 of t is equal to alpha 1 beta 1 into a into cos omega 1 of t plus cos omega 2 t plus I have 3 by 2 alpha 1 alpha 2 beta 2 plus 3 by 4 alpha 1 cube into beta 3 plus 3 by 4 alpha 3 into beta 1. All these things as the coefficients for the cubic term, a cube cos omega 1 minus 2 omega 2 t plus cos 2 omega 2 minus omega 1 into t. So with this, if you write IIP3, I'm just repeating what we have done before. We know the expression is 4 by 3 into alpha 1 by alpha 3. But now when we write for this combined system, that can be written as 4 by 3 into alpha 1 beta 1 divided by the same terms. 2, I'm just adjusting these terms here, 2 alpha 1 alpha 2 beta 2 plus alpha 1 cube into beta 3 plus alpha 3 into beta 1 the whole cube, right? So if you proceed from here, you will definitely the analysis what we have done before, and this will definitely lead to the same thing. And now probably you can appreciate why I said that in narrowband system, the term, this term will not be there. maybe I think now you can clearly say that, right? So if the system is narrow band, these terms like omega 2 minus omega 1 and 2 omega 1 and 2 omega 2, these terms will not be present at the output of first stage if the system is narrow band. In that case, no need to consider the third term, or we can confidently we can say that in narrow band systems we can actually neglect this term, because this term is available at the output as a result of or due to the presence of second harmonic and IM2 terms at the output of first stage. This is produced as a result of IM2 and second harmonic terms at output of first stage. I hope this is clear, and hence I can say that in narrowband systems, alpha 1, alpha 2, beta 2 term can be neglected. So I am neglecting with proper reasoning, right? All right. So if you have doubts, you can ask. Thank you so much for joining.